and so we're going to now talk about a specific type of reaction. We're going to use what we learned about equilibrium to help us explain certain classes of reactions. And the first one that we're going to talk about is from chapter 14, acid-base reactions. All right. Acid-base reactions are something that you cover over and over and over again in chemistry. They're a very important class of reactions. You talk about it a tiny bit in Chem 1A. You are going to build on that here in Chem 1B. When you get to organic chemistry, that's going to be a topic that they cover yet again in a little bit more depth. All right, so just a very important class of reactions. Previously in your Chem 1A course, what you would have learned is this category of double displacement reactions, and how acid-base reactions fit into that category. All right, let's just note, this is our Chem 1A. All right, so given an acid, HCl, our acids and bases are aqueous, and a base like sodium hydroxide. All right, in these double displacement reactions, you would swap out the hydrogen and the sodium, swap your cations here, and you would have learned that this creates aqueous sodium chloride and liquid water. All right, and this was kind of what was hammered home about these acid-base reactions, was that an acid plus a base, they combine to make a salt and water. All right, and that's true for a very limited subset of acids and bases. The world was defined to you in terms of acids and bases. Of acids contain H plus, and bases contain OH minus. All right, this was the definition of an acid. This was the definition of a base. This is what's called the Arrhenius definition. Okay, so it wasn't a total lie, but it was a really small window into this class of reactions. And so what we're going to do is we're going to expand our understanding of acids and bases. All right, what we're going to be using now for our Chem 1B is what's called the Bronsted-Lowry definition of acids and bases. All right, so in our Bronsted-Lowry definition of acids and bases, an acid is defined as being a hydrogen ion donor and a base is defined as being a hydrogen ion acceptor. All right, so an acid is anything that donates a hydrogen ion, and a base is the thing that accepts that hydrogen ion. Your Arrhenius definition here, it works. Your base, your hydroxide, is accepting that proton of water. So all of our Arrhenius acids and bases are also Bronsted-Lowry acids and bases, but we're going to see that this definition applies to even more acids and bases. All right, I will say this little O in Bronsted is like a German name or something. I don't know, it has a little slash through it. Okay. The other thing is we don't call hydrogen ions hydrogen ions. All right, let's think about it. If I'm holding a hydrogen atom in my hand, it's got one proton and one electron. All right, the vast majority of hydrogen out there is just one proton, no neutrons, right? Hydrogen 1. So if I make a hydrogen ion and I take that electron away, what am I left with? Just a proton, all right? And so these hydrogen ions, we don't call them hydrogen ions, we call them simply protons. So an acid would be a proton donor, and a base a proton acceptor. All right? So let's look at an acid-base reaction that would not follow our Arrhenius acid-base definition. All right, we're going to take HNO3. This is nitric acid. So this is going to play the role of our acid in this reaction. And our base, we're going to use an organic base, ammonia. Well, again, by the definition of what an acid is, this acid is going to donate a proton, right? It's going to give up this hydrogen right here. So that means on the other side, my nitric acid loses its proton and becomes just the nitrate ion. All right, and even though nitric acid is neutral, what it lost was a positively charged hydrogen ion, which means that what I'm left behind with has that negative charge, HNO3 minus. All right, so what we're going to note is that our acid is going to lose a proton. So we're going to decrease the number of hydrogens by 1. And since that hydrogen that we lost had that positive charge, we also have to decrease our charge by 1. All right, that's how I turned my acid formula here into this nitrate ion. All right, my base, NH3, is going to accept a proton. So now I'm going to increase the number of protons in that formula. So this is going to become NH4. Oh, whoops, I'm going to be good here. This is aqueous. This is aqueous. All right, importantly, I increased my number of protons by 1, or my number of hydrogens by 1. And since it accepted that positively charged ion, it went from being neutral to having a positive charge. All right, so how did I get my formula here? I took my base formula and I increased my number of hydrogens by 1. And I increased my charge by 1. All right, we got some special terminology for our products here. Our acid gets converted into what we call the conjugate base. And our base gets converted into what we call the conjugate acid. All right, and this is going to kind of be our first step. Like, given an acid and a base, we need to be able to predict our products here of these acid-base reactions. All right? Again, our acid, by definition, is playing the role of a proton donor. It's going to lose this hydrogen here. So we're going to decrease its formula by 1 hydrogen and decrease its charge by 1. That gives us what we call our conjugate base. And our base turns into our conjugate acid. We take our base, it's going to accept that proton. So its formula is going to increase by 1 hydrogen, and its charge is going to increase by 1. All right? So why is it that the acid and the conjugate base are paired and the base and the conjugate acid are paired? That seems kind of backwards here. All right, but remember, we've updated the way that we look at chemical reactions in this course, where we're no longer just looking at them as going in one direction. And if we were to look at this reaction in the reverse direction, what would be playing the role of the acid, what would be playing the role of the proton donor would be your conjugate acid. And what would be playing the role of the base, what would be accepting the proton, would be your conjugate base. All right, so that's where that terminology comes from. All right, when we look at the reaction in the reverse direction, our acid, our conjugate acid, is being the acid donating a proton. When we look at the reaction in the reverse direction, our conjugate base is playing the role of the base and accepting that proton. Okay, so step one, we're going to practice these conjugate pairs here. All right, by that I mean I'm going to give you the formula for an acid, and you're going to give me the formula for its conjugate base. Okay, and so just starting out with that same acid that we looked at previously, so we can just kind of remind ourselves how we got that formula. What we said is we were going to decrease the number of hydrogens by 1 and decrease the charge by 1. So I took this formula of HNO3, I got rid of that hydrogen. It only had the 1, so I took it away. And it went from being neutral to having a negative charge, right? Decreased my number of hydrogens by 1, decreased my formula by 1. Okay, so now we're going to play this game here. I want you to give me the conjugate base of the following. All right, so I'm going to take my formula here. It's got this 1 hydrogen. I'm going to decrease my number of hydrogens by 1. So now I got none of them. And I'm going to decrease my charge by 1. Since it was neutral, it's going to become negative. All right. Hydrogen sulfate here. I got my hydrogen. I'm going to get rid of it. So now I'm just at SO4. And what's the charge going to be? -2, because I started out with a -1 charge, went down to -2. All right. And then the last one here is water. The water can play the role of an acid in a chemical reaction. And I guess let me just say that that's kind of what we want to be thinking about now. Rather than acids being like a category of molecules, right? There definitely are molecules that have that word acid in there, and that's because they play the role of the acid all the time. But really what we're updating our thinking is the role that these molecules are playing in this chemical reaction. Is it donating a proton or accepting a proton? water is not something that we typically think of as an acid, right? I mean, if we spill water on ourselves, we're not too terribly worried about it. We're not grabbing a spill kit or anything like that. Nonetheless, water can play the role of an acid and does often play the role of an acid in a chemical reaction because it donates a proton. All right, so if we did our formula here for our conjugate base, we would decrease our number of hydrogens by 1. So instead of 2, I'd only have 1. We decrease our charge by 1. So OH, or this molecule is more commonly written as OH minus instead of HO minus. And because we're talking about water's conjugate base, this molecule is famous and has a special name. This is what we call a hydroxide ion. All right. Now, most of our acids, a lot of our acids that we're going to encounter are these inorganic acids, and they always have these hydrogens listed first. All right. There's a little bit of a different convention for our organic acids. All right, and what it means to be an organic acid is that it contains carbons and hydrogens. If you've ever heard of that branch of organic chemistry, an organic molecule necessarily contains carbons and hydrogens. All right, so a good example here would be acetic acid. This is the active ingredient in vinegar, CH3COOH. All right, where here our acidic proton is listed last. Okay, so what we're going to do is make a note here that in these formulas for our acids, that donatable proton is always listed either first in the formula or last in the formula. That's the one that you're going to get rid of when you're creating your conjugate base formula. All right, this is our donatable proton. All right, donatable protons, always listed either first or last in a chemical formula. All right, so given that, everybody take a second and give me the conjugate base of this organic acid here. So since that's my donatable proton, when I decrease my number of hydrogens in my formula, that's the one I'm going to get rid of. All right, and then I'm going to decrease my charge by 1. So here is the formula for my conjugate base. Notice I didn't touch these hydrogens here because they weren't the ones that were listed either first or last in that molecule. All right. Okay, let's play the same game now, but with some bases. I'm going to list a base, and you're going to give me its conjugate acid. All right, we'll start out with that first example that we had done so we can remind ourselves how we did this. That acid was NH3, or ammonia. And what we did was we took that base formula and we increased our number of hydrogens by 1. And we increased our charge by 1. All right, so now my formula here is NH4 with a plus sign. All right, so let's do a few more here. I'm going to do F minus CO3 minus 2 and water. All right, so I'm again going to take my base formula in order to get my conjugate acid. I'm going to add a hydrogen, and I'm going to increase its charge. In this case, since it was -1, it'll increase to 0 or be neutral. All right, this carbonate ion, it's going to accept a proton and become HCO3, and what would its charge be? Minus, because I'm going to increase it by 1. So it goes from being -2 to -1. All right, and then lastly, water. You know, we noted that water can play the role of an acid in a chemical reaction. Water also can play the role of a base in a chemical reaction. It can be the one that's accepting protons. And so it's going to increase its number of hydrogens by 1. So now I have H3O, and increase that charge by 1 has a plus charge. All right? And again, because we're talking about water here, its conjugate base is famous. I'm sorry, its conjugate acid is famous. This also has a name. This is the hydronium ion. We're going to talk a lot about hydronium in this chapter. All right, and we kind of already did an example here, but let me just note, you know, I listed it at the front in some and at the back in another. So what's going on here? Again, these are our organic bases. All right, our organic bases, they contain carbons and hydrogens. And often there's one element that loves to play the role of a proton acceptor, and that's nitrogen. Okay, so a good example of an organic base is what's called methylamine, CH3, NH2. All right. And similar for what we noted before, where do we add? We know we're going to take this formula and increase our number of hydrogens, right? But where are we supposed to do it? I have hydrogens here and hydrogens here. All right, importantly, we're going to list, okay, let's just say, these accepted protons are listed either first in your formula or with the nitrogen. The nitrogen is the one that's actually accepting that proton in this molecule. So if I was going to do my conjugate acid formula, I would say CH3. I wouldn't touch the hydrogens associated with the carbon. I would increase the number of hydrogens associated with my nitrogen here. So this would be CH3NH3+. All right, so we listed it with our nitrogen here. And just to kind of draw some Lewis structures and see why this is important, we don't talk too much about structures in this course, whereas when you go on to organic chemistry, that's like the only thing you talk about. All right, but just to be clear, there's a reason why we list it the way that we do, and that is because the carbon has these three hydrogens bonded to it. My nitrogen has 2, and it has this lone pair, Well, if we did the formula, rather the Lewis structure for our conjugate acid here, what has accepted that proton is that nitrogen atom. All right, so we list it with our nitrogen because nitrogen is the one in an organic base that's accepting that H+. Cool. Okay, so what we need to do is be able to predict an acid-base reaction, right? Given an acid and a base, what are the products? What are my conjugate acid and my conjugate base? Okay, so let's practice real quick. I'm going to put down an acid-base reaction here. All right, I'm going to tell you that this is playing the role of the acid and this is playing the role of the base. And you need to give me the products of this reaction. You need to tell me what my conjugate acid and conjugate base are. If I'm trying to get the formula for my conjugate acid, which one of these do I look at? My acid or my base? My base, right? My base is the one that is connected to my conjugate acid. My acid is going to tell me what the formula is for my conjugate base. All right, so looking at that base, in order to get my conjugate acid, I'm going to take that formula and increase my number of hydrogens by 1. So this will become HPO4. And I'm going to increase that charge by 1 from from -3 to -2. In order to get the formula for my conjugate base, I take my acid and I decrease the number of hydrogens by 1. So now I'm just left with that iodide. And I decrease its charge by 1, so I-. Okay? So given these conjugate pairs, how we take our acid and decrease its number of hydrogens by 1, decrease its charge by 1. We take our base and increase its number of hydrogens by 1 and increase its charge by 1. That's how we're going to predict the products of our acid-base reaction here. All right, what are our conjugate acid and our conjugate base? Okay, cool. We're going to play this same game again, but we're going to look at a really important reaction in this chapter, what's called the autoionization reaction. All right, so in this reaction here, we have water playing the role of the acid. But it is reacting with yet another water molecule, which is playing the role of the base. All right, I'm going to be good and put my equilibrium arrows in here. I'll explain why here in a second. But right now, you're going to work on giving me the conjugates for this reaction here. What are my products of this reaction? so to get our conjugate acid, we're going to look at that formula for our base. We're going to increase its hydrogens by 1 and increase its charge by 1. What's up?
When we're writing the rising side, does it matter which one goes first?
No, you can always swap these things in your chemical equation. You also don't have to do acid and base. I kind of maybe just like have a one-track mind the way that I do it here, but the order in which you organize things in a chemical equation don't matter. All right, so my conjugate acid, we talked about this earlier. We even gave it a special name. What's my conjugate acid in this autoionization reaction? Hydronium. And our conjugate base, we also have a special name for, what is that one? Hydroxide. Okay? So this is a really important reaction in this chapter. It turns out that in every aqueous solution, in my water bottle right now, water molecules are reacting with one another to create hydronium and hydroxide. All right? So now we're going to look at the equilibrium constant for this reaction. Because it's water, it gets this special designation of, instead of being Kc, Kw. All right? And we're going to build our equilibrium expression, but in order to do that, we got to be good and we got to put in our states of matter. Okay? While my water is a pure substance, it's got that pure liquid designation there. My hydronium ions are now floating around in that aqueous solution, just like my hydroxide ions. So both of these are aqueous products here. All right, so now given what we discussed last chapter, everybody's going to take a second and build me that autoionization expression here. All right, my equilibrium expression for this autoionization reaction. All right, so equilibrium constants, what do we remember? What over what? Products over reactants. Awesome. But what from this equation isn't going to appear in my equilibrium expression at all? My waters, my liquids, right? So my equilibrium expression here is the concentration of hydronium times the concentration of hydroxide is equal to that equilibrium constant Kw. Right? My products over reactants, but my reactants don't appear in this equation at all. All right? Now, just like with every reaction, we can go and we can look up this equilibrium constant. It is a constant value, all right? And for this particular reaction, this autoionization reaction, that value, that equilibrium constant, is 10 to the negative 14. So what would we say about this reaction? Does it favor the products or the reactants? The reactants. And does it strongly or weakly favor the reactants? Strongly. So this reaction doesn't happen a ton, don't get me wrong. Right? It's not like a super favor, but it's not like all my water molecules are falling apart into hydronium and hydroxide. This equilibrium very much so favors this direction here. But nonetheless, this is a really powerful equation and going to be very important in this chapter, because what it says is that the concentration of hydronium times the concentration of hydroxide in my aqueous solution is always equal to the same number, that 10 to the negative 14. Which means if I know one of these, I can always find what the other one is as well, because their product has to equal that same value. All right? So this here is true for every aqueous solution. Okay? And practically what that means is if we know the concentration of hydronium, we can find the concentration of hydroxide and vice versa. And what we're going to see is the name of the game in this chapter and the next chapter is going to be all about trying to figure out what the hydronium ion concentration is in our solution. All right, we'll talk about pH here in a second. I think everybody's heard of pH. pH is the amount of hydronium that you have in your solution. So this is going to be really helpful here in finding out how much hydronium we have. All right. The other thing, I'm going to lie to y'all, just because it's going to make our lives so much easier. Equilibrium constants are absolutely measured values, okay? But for the purposes of our course, just to make our life easy, we're going to pretend like this specific equilibrium constant here is an exact value. That 10 to the 14 is not going to limit our sig figs. It's an exact number, all right? Okay, so let's use this autoionization equation. All right, a solution has a concentration of hydronium equal to 0.045 molar. All right, what is the concentration of hydroxide in our solution? All right, so I'm going to take my autoionization relationship, my concentration of hydronium times the concentration of hydroxide equals that same 10 to the negative 14. And I need to solve this equation for that concentration of hydroxide. And whenever we're trying to solve for something, that means we need to get it all by itself. So I need to move the other thing to the other side. How am I going to move this concentration of hydronium over to the right-hand side of my equation? I'm going to divide both sides by that concentration of hydronium. All right, remember we can do anything we want as long as we do it to both sides. So this concentration of hydroxide is 10 to the negative 14 divided by that hydronium concentration. All right, and so we're going to punch this into our calculator. And we get 2.22222 repeating. We're going to put our two sig figs on there, times 10 to the negative 13 molar. All right, so again, our autoionization relationship here says that if we know one of these two concentrations, we can always find the other one, because their product always has to equal that same magic number, 10 to the negative 14. Cool. All right, so we use this different way to talk about, so again, we're going to be very concerned with what the concentration of hydronium is in a bunch of different solutions. That's the game we're going to play throughout this particular unit. But there's a specific way in which we talk about hydronium ion concentration, which is what we call the pH of the solution. All right, and the most important thing that we're going to note about pH is the information that you get from a pH. The pH of a solution is 4, for example. All right, what that is telling you is the concentration of hydronium just on a log scale. All right, so what exactly do I mean by that? Well, these hydronium ion concentrations can differ dramatically from solution to solution, all right? Meaning that we could have this huge range of solution concentrations when it comes to our hydronium concentration of, let's say, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5, 10 to the negative 6, etc., right? Differing by an order of magnitude, right? A factor of 10. If we convert this to pH, all right, our definition for pH here, do this up here, pH is equal to the negative log of that hydronium ion concentration. All right, so if we take these same concentrations of hydronium ions here, but we put that on our log scale, we take the pH of that solution. The pH of a solution where the concentration is 10 to the negative 3 would be 3. 10 to the negative 4 would be 4. 10 to the negative 5, 5, etc., etc., etc. All right, so since we're dealing with differences in concentration of hydronium that are enormous, right, on like orders of magnitude, we find it more convenient to use this pH scale, this log scale. And I know everybody out here does not find logarithms to be convenient in the slightest, all right? But there is some method to the madness in terms of how they, why they do this. Again, makes your life a little bit easier. Rather than talking about huge changes in concentration, orders of magnitude changes, you're talking about small changes on that log scale. All right? Now, importantly, we're going to do the reverse here. So this is our definition of pH. Let's just say if we were going to do the inverse of this, so this would allow me to calculate what pH is given my hydronium ion concentration. If I was instead given a pH and I wanted to work backwards to find hydronium, I would have to do the inverse of this equation here. All right, and again, since logs suck, let's just kind of put it down here. Okay, if I were going to do the inverse of this equation here, that would be 10 to the negative pH would give me my hydronium ion concentration. All right, so if you remember back to your your logarithm algebra, these would be inverse of one another. Okay? Cool. So then let's go back here. We did this example. I gave you the concentration of hydronium. I asked you what the hydroxide concentration was in the solution. The other thing I could ask you is, what is the pH? All right, so everybody take a second, track down, that's going to be very important in this particular chapter, that log button on your calculator, and make sure that you can get the pH of this solution here. All right, so we got this new formula here. pH equals the negative log of our hydronium ion concentration. Since I knew my hydronium ion concentration, I'm going to plug this into this formula here. All right, so I'm going to take the negative log of that 0.045. And my pH here, my calculator spits out 1 point. I'm just going to put on a bunch of digits on there for right now. I get 1.34678. Okay, so first of all, make sure that you know your log button on your calculator. We're going to be taking a lot of logs in this particular unit. All right, so the negative log of that hydronium ion concentration gives me the pH of that solution. Now my concentration units were units of molarity. So what about pH? pH is kind of a weird quantity here. It is a unitless quantity. All right, which gives me a lot of anxiety just having that naked number there. So I just like to write pH equals. It makes me feel better. All right, but there's no units that we tack on to the end of a pH. In fancy chemistry speak, it's what's called an activity. It doesn't actually have any units associated with it. All right, and now I just put down a whole bunch of extra digits here. We have talked about addition, subtraction sig figs. We talked about multiplication, division sig figs. Well, those are different because those are considered different operations in the world of mathematics. Well, guess what? Logarithms are also a different operation. So with this new operation comes new sig fig rules. All right, so let's say pH and sig figs. And honestly, it's not that bad. It's more just a pain in the butt that we have yet another rule that we got to know here, but the rule itself isn't too terribly crazy. All right? The rule is that the number of significant figures in our concentration of our hydronium is going to equal the number of decimal places in our pH. All right, so if we go back to our particular example here, we're going to look at our input. Our input of 0.045 had 2 sig figs. So that's going to be, once we take that log, when we're carrying our sig figs, it's now going to correspond to 2 decimal places in that pH space. All right, my number of sig figs in my concentration equals the number of decimal places in my pH. All right, let's just put here, number of sig figs equals number of decimal places. All right, so if I'm going to report the pH of this solution to the correct number of significant figures, I'm going to say my pH equals 1.35. And what are my units? Trick question, no units on pH, right? A unitless quantity. So we just leave it as a naked 1.35. Cool. All right, we also have these like classifications that we use given whatever the pH of our solution is. All right, these pH ranges. We would classify a solution as acidic all right, an acidic solution means that the concentration of hydronium is greater than the concentration of hydroxide in that solution. Okay? And given that we know that the concentration, that the product of these two always has to equal that same magic number, 10 to the negative 14, that means that an acidic solution would have a concentration of hydronium that's greater than 10 to the negative 7. And if instead we put that on our log scale, on our pH scale, that would be the same thing as saying that the pH of this solution is less than 7. Remember, pH is a negative log, so that's how my sign got flipped here in my equality. All right, likewise, we would call a solution a basic solution. If the concentration of hydroxide was the one that was greater, concentration of hydroxide is greater than the concentration of hydronium. All right. And again, since the products always have to equal that same magic number, 10 to the negative 14, we can convince ourselves that that means that my hydronium ion concentration would have to be less than 10 to the negative 7. All right, and if we put that on our pH scale, a basic solution is when that pH is greater than 7. All right, so these are all saying the same thing. All right, an acidic solution has more hydronium than hydroxide. That means it's got, well, it should be good here. Concentration of hydronium greater than 10 to the negative 7. We should be good and put our units. Concentration does have units. All right, and if we put that on our pH scale, that means the pH of this solution would be less than 7. A basic solution has more hydroxide than hydronium. So that means its concentration of hydronium would be smaller than that 10 to the negative 7, which means that its pH, if we put it on that pH scale, pH would be greater than 7. All right, and then lastly, if we had a neutral solution, that means that the concentration of hydronium is equal to the concentration of hydroxide, which has to be, given that the fact that they have to be, the product has to be 10 to the negative 14, they both would have to be 10 to the negative 7 molar, which means that the pH of a neutral solution would be 7. Okay? So what would we say about our solution that we made here? Is this an acidic or a basic solution? An acidic solution. First of all, the concentration of hydronium was way more than the concentration of hydroxide. All right. I also had that pH less than 7. Okay. So both of these pointing to the fact that this would be an acidic solution. Cool. All right, so we're going to talk about a very special type of reaction, what's called an acid dissociation reaction. Okay. This is what happens when you take an acid. So any acid, if you take that acid, you're going to combine it with water, meaning if my acid is my acid, what role is water playing in this reaction? The base. All right, let's leave some room here, and we're going to kind of prove to ourselves, given what we discussed about conjugate pairs, what the rest of this formula should look like here. All right, I'm going to take an acid. We're going to take hydrobromic acid. I'm going to combine it with water. Water, of course, is that pure substance. And everybody's going to take a second and give me the product of these reactions. Right, since water is my base, in order to get the formula for my conjugate acid, I'm going to increase the number of hydrogens by 1 and increase the charge by 1. And this we said was this famous molecule. It's got a famous name, hydronium. And in this case, my conjugate base is this bromide ion. All right, so in these acid dissociation reactions, you're always adding some acid to water, and that's always going to create hydronium and whatever your conjugate base is. This will depend on what acid you use. Okay? These reactions, again, we're going to talk about them for a bunch of different acids. Combine an acid with water, get hydronium and some conjugate base. Because they are this famous set of reactions here, we have this special designation for the equilibrium constant. We would call it a Ka value for the acid dissociation reaction. Okay? And that Ka value, that equilibrium constant, is tabulated. That's going to be one of our constants page for this chapter. We're going to have a list of a bunch of different acids. Each one of them is going to have a different Ka value, and that corresponds to the equilibrium constant for these acid dissociation reactions. What happens when we take that acid and add it to water? All right? And if I care about the pH of my solution, which one of these am I going to be trying to quantify here? That hydronium ion concentration, right? If I know this, I know the pH of that solution. So that's the name of the game, right? That's the game that we're going to be playing for like the next 2 weeks here, is how much hydronium product is formed in this reaction. If we know that, then we can calculate the pH of that solution. All right? So we're going to start with the easiest one here, with the easiest set of acids to work with. And those are what are called our strong acids. A strong acid is classified as a strong acid because it has a very large Ka value. Right? I'm talking like 10 to the 10 or something like that. Some huge number. All right, so if we have this ginormous number for our equilibrium constant here, what would we say about this reaction? Does it favor the products or the reactants? The products. And does it strongly or weakly favor the products? Strongly. So these are reactions that strongly favor the products. All right, so much so that in our treatment of these strong acid solutions, we're just going to pretend that these reactions go 100% to completion. That every single one of your strong acid molecules get converted into hydronium and conjugate base here. All right, and that's going to make our life a lot easier in terms of the calculations. We're not going to treat this like an equilibrium problem. All right, we're going to say that this dissociation reaction goes 100% to completion. All right, and why is that going to make our lives so much easier? Because it means whatever the concentration of strong acid that we start out with initially, as soon as we put it in water and it reacts in this acid dissociation reaction, 100% of it gets converted into hydronium ions, which means that whatever amount we started with, that's going to be our concentration of hydronium at equilibrium. All right, so strong acids here. In a strong acid, we're not going to have to treat this like an equilibrium problem. We're going to do it more like a Chem1A stoichiometry kind of problem where you're just assuming 100% of this reaction happens, meaning every bit of that strong acid that I start with is going to be converted into hydronium and conjugate base. And of course, the hydronium is the one that I'm interested in because that'll help me calculate the pH of that solution. Okay, so then how am I supposed to know what a strong acid is versus all the other acids in the world? All right, HBr is a good example here. It's kind of a good news, bad news thing. You just got to know them, but it's not that big of a list. All right, so we're going to have this list of 6 strong acids that we just got to know are strong acids. All right, so this is our strong acid list. This is something we just need to know. Cool. All right, a few of them know here. All right. Yeah. So our strong acid list, this is this list of 6 that we need to know. Sometimes there's a 7th one on there. We're just going to keep it to these 6 here. All right. So 3 of them are our halogens. So HCl, HBr, and HI. All right. That would be hydrochloric, hydrobromic, and hydroiodic acid. All right, so hydrogen paired with one of those halogens. All right, the other ones are hydrogen paired with these polyatomic ions, HNO3, H2SO4, and HClO4. HNO3 is what's called nitric acid. H2SO4 is what's called sulfuric acid. And HClO4 is what's called perchloric acid. Sometimes chloric acid is added to this list, HClO3. We're going to keep it to these 6. What's up?
When we're doing like the online assignments for this, is it going to be limited to these 6, or are we going to have that extra one?
No, it's just going to be these. These 6 are in my course. Yeah. Okay. So these are our 6 strong acids. This is our list here that we just got to know. All right, so let's take this list, kind of combine everything that we've talked about up until this point. All right, you're going to tell me what is the pH of a 0.45 molar solution of perchloric acid. All right, so how am I supposed to do this here? I know my concentration of HClO4, that perchloric acid that I have initially, is equal to that 0.45 molar. But since this is a strong acid, 100% of those perchloric acid molecules will dissociate into hydronium ions, meaning that that's going to be the concentration of hydronium that I get when this reaction reaches equilibrium. And if I'm looking for the pH, I need that negative log of my hydronium ion concentration. All right, so everybody's going to take a second, tell me what the pH of this solution is, and then you're going to report that pH to the correct number of significant figures. All right, so I punch that into my calculator. I get a pH of 0.34678. Again, what are my units? No units. All right. And then my input here has these two sig figs. So that's going to correspond to two what in my pH? 2 decimal places in that pH, or 0.35. All right. So the last thing that we're going to do here, we're going to go back to this auto-ionization relationship. All right, and we're going to do some algebra to it. We're going to put our auto-ionization on that log scale. All right, what do I mean by that? I mean I have this auto-ionization relationship. Talking a lot about logs here. So we're just going to take this equation and we're going to do a bunch of algebra to it. All right, remember I can do anything I want to this equation as long as I do it to both sides. So what I'm going to do is I'm going to take the log of both sides of this equation. All right, so over on the right-hand side here, the log of 10 to the negative 14, 10 to the negative 14 is just a number. So if I take the log of the negative log rather, sorry, we're going to take the negative log of both sides. If I take the negative log of that 10 to the negative 14, that turns that right-hand side into 14. All right, you can convince yourself that just by punching that into the calculator. All right, on the left-hand side though, we're gonna have to use this identity that logs have. Log algebra is always really funky. I used to have a math teacher that would say, in the magical world of logarithms, all right? In the magical world of logarithms, the log of A times B is the same thing as the log of A plus the log of B. All right, So now I have my log of this product here. I'm going to break it up. So it's the log of the sum of both of them. The log of the concentration of hydronium, or rather the negative log of the concentration of hydronium. All right, plus the negative log of the concentration of hydroxide. Okay? But the negative log of the concentration of hydronium, we have a special name for that. What is that? The pH. All right, and so what we're going to do is we're going to similarly define the negative log of the concentration of hydroxide. We're just going to give this a fancy name as well. This is the POH. All right, and so our auto-ionization relationship on the log scale is pH plus POH equals 14, that magic number 14. All right, the reason why we do that is sometimes it's going to be more convenient to convert using this equation here. Other times it's going to be more convenient to convert using our original auto-ionization relationship. You could actually always do either, it's just sometimes it would be more steps, all right? What you're going to find is you're probably going to prefer the latter one that we did, rather than this multiplication one, but it really is going to depend on the context. Cool. All right, we'll pick this up next time.